In our beam mass experiment, what we want to do is use an accelerometer to evaluate our, our model of the system. We've got the beam. We're attaching a mass to it. We're going to attach a little accelerometer on here that gives us a signal. And if you look right here, Den Hartog is a reference there you can find at the end of the slides. Tells us that you can estimate the undamped natural frequency as shown right here by taking the known mass m, right, and the mass of the beam, in this case little m, is maybe known, and so you could get a better estimate of the undamped natural frequency if you include about 0.23 times that mass of that beam. So we want to check that. This formula actually, you can, if you look at Den Hartog, that's derived using an energy method. It's actually a pretty good estimate. So we're going to test that. And again, it's all part of how good of a measurement you're making. Now, in order to do that, and there's certain things when you either analyzing a system or design, there's certain things you can estimate pretty well. The mass, sometimes you can weigh it directly. Stiffness, possibly, here the stiffness, cantilevered beam, if we know these parameters, we could estimate that. But sometimes not. We'll see how close we can get. So as we're trying to estimate undamped natural frequency, how do we do that? Well, first, let's say we just try to make a rough estimate. You could always say, I don't know, the beam mass. Get a sort of an estimate just with the known mass, the tip mass m. Sorry, I'm using little m here, but that's the, if you say a massless beam with some mass at the end, and that would give you one estimate. That's going to be high, right? Because you're not including the beam mass, so that gives that as an upper bound. And another estimate would be, well, just give it the whole mass of the spring, or in this case, the beam, and that'll give you a lower bound. And that the actual value is going to be in between, so you could at least have upper and lower bounds, and that's sometimes a good way to estimate things. Sometimes point estimates are not the best way to go. Now, when you're trying to estimate or measure the undamped natural frequency, be mindful that even if the oscillations look like they're not damped, they are damped a little bit. So there's going to be a little effect of damping in there. So you never truly measure T sub n, which is the undamped period. You're always going to have a little bit of damping in there. So the effect of zeta is in there, and so even if you could just from measuring peak to peaks, say, get an estimate of the period, you could get omega d. You wouldn't be able to estimate omega n because you need to know zeta. So one way to do that before you get omega n is let's estimate zeta, and I'm going to show you a method that's very popular for doing that. Oops. It's called the logarithmic decrement approach. This is an experimental way of determining damping ratio. And what we do is you can do this for any system. Let's say you had a vehicle and you wanted to know what the suspension damping was. You could, in the sense, you got a spring in there, you got a damper, and you wanted to get the zeta of your damper. You could depress this guy and then let it go, and it's going to oscillate. It's basically an initial condition response. So you assume it's underdamped because it's decaying exponentially. So it's going to follow this response formula that we predicted before. And x dot is going to be 0 if we release from rest, right? So we don't need to know that guy. So the actual formula for x of t, is just this decaying exponential with a cosine. And it turns out that, and I won't go through the details here, you can look at the slides, that all you have to do, in fact, to estimate zeta is really just measure the peaks, all right? So the amplitude of the response, right? All you want to know is measure this envelope, follows a decaying exponential, okay? And it's a function of the initial conditions and zeta, right? So you can show that the amplitude decay can be determined, right, using just the peak values every tau d seconds, right? So you can say, you can take the amplitude at n, and then the amplitude at the next, so let's say this is n and this is n plus 1. That ratio is just this exponential, okay? And then the period between the peaks is known, right? So taking the log of both sides of that relation up there, you can show that this is why it's called the log decrement, that the log of the decrement, an over a sub n plus 1, has to follow this relation. And here is the cycle number, right? And note that this looks like a slope, right? So essentially what we do is we plot for every n, you plot this value here versus n, and then it shows that the slope of that line is linear, right? And it's going to be linear if your model was valid. If you don't have a linear system, it's not going to decay exponentially, and it won't follow a linear trend. And I'm going to show you that in a second. All right. So here's an exponential decay, right? And you'll see when, you know, it should look exponentially, and that's a linear case, right? If you see that the data decays, you know, like with a linear slope, that actually means that you have a nonlinear system. Like this will not follow a log decrement. Okay, so looking at the data, it's the other way around. You have a nonlinear decay here for a linear system, a linear decay for a nonlinear system. And let me show you two different cases. When you plot the data, right, here's a log decrement in two cases. This was a case where I had actually a linear system. Here's the n for each cycle, plotting that ratio. A0 is the first one, and you plot all the subsequent ones taking n, and you plot it versus n. And note, you get a nice linear trend. Get the slope of this guy here, and that's going to be, you know, let's call that beta. Okay, that slope using a basic linear regression can be used to find zeta, and I'll show you the formula in a second. If you plot this log decrement and you don't get something like a linear trend, that means that a linear model, a linear damping model does not work. Okay, so you might get something that looks like this. Right, so it's another way of checking, hey, is my model, is my linear assumption, linear damping assumption good? Well, if you get this, then it's not linear. Not linear damping, rather, right? So once you have that slope, then you can solve for zeta, right? It's a little, it's a quadratic, so you have to do a little, but you can find that, right? Nice quick approach. And let me show you over here. I give you a little code, and what I did is I set up this little Python script, and I just put in the perfect, you know, I calculate a nice perfect, you know, response, and this, you'll see that I'm just putting in, you know, a made up undamped natural frequency. I'm gonna calculate it for a number of cycles, 10. I found the final period, the final time step, just so I can get a time vector. I give it a value of zeta. It has to be less than 1 for it to be ultra-damped. I compute the damped natural frequency. I compute this value I call psi d, which is the other term in that equation. And then I just compute the response, the undamped response, using that formula. There's U naught as if it was a step, but we don't have a step, so I should just make that 0. I made that 0, I should just left that out. And then what I'm doing is I'm using a really nice script. Note I import it here from scipy.signal. There's a function called find peaks. Just you can search online for that. But this is the way you use it. It puts in peaks here, the indices, or the values of the peaks of sorry, let me start over. You use find peaks with XU. You have to give it some options here. For example, you might have to tell it a couple of different things. There's a bunch of options here. Look at the help. Sometimes if you have a noisy signal, you have to be careful. For something that's kind of very clear peaks, it's pretty good. But sometimes you tell it, don't look for peaks above a certain level. Also, you might tell that if you found a peak, you don't look for another peak for another number of points. There's some options like that that you can find online. So look up, just search on, for the find peaks function, and you can find additional options you could put here to make it find things better. It'll come back with the places where the peaks are located, and then this will give you the value of the peaks and just have a little this comprehension here, and then and you can script this in a bunch of different ways. And then I'm finding the times and the amplitudes, and then I'm going to then plot the data with the superimposed peaks on there. I'm just going to run this so you can see what it does. Again, you can study this, and what it does is it finds those peaks. Now what you can do is use these APs, and the APs really gives you the cycles. If you see that it finds, and what I do is I put little X's where the peaks are, and that way you can see how it is. This script only finds the peaks. If you want to now find the damping using this, for some decaying data like you measure in the lab, then, sorry, I'm putting blue X's where the peaks are. See how nicely that is? You could always just plot your data and then go in here, and you can see down here, and find the peaks values and do this all manually. But hey, Find Peaks does this for you. You can do it automatically. If you had a bunch to do, it's nice to automate it. Of course, you could always just do this manually. Find the peaks by just reading the values there down below. Make a little script, use it in your linear regression, and you can find zeta. Once you find zeta, right, then you can go back into your formula for the damped natural frequency, right? And you can estimate this from measuring tau sub d. You've got this guy here, zeta, from log decrement, and so now you've got a good estimate of omega sub n. Remember that omega sub n is going to be, some k over some effective mass. So you can see what that effective mass is. Does it follow that formula from Den Hartog? It's part of it is the end mass. Maybe the other part is some fraction of the beam mass. And does it follow that formula? Remember, this is all about how well can you make measurements, how close can you come to that theoretical value. Always remember, if you've made all your measurements well, then the experimental value is what you trust, right? And you want to see how good that theory is, because if that theory gives you some confidence, now you can use that in future analysis, right? You don't want, it's harder to run experiments, but this could give you some confidence in using a result like that.